Assalamualaikum to Professor Madya IRTH Dr. Faizal bin Sheikh Ali. So today I will present about development of a Python-based program for structural analysis using a moment distribution method. We are from Group 3 and our group member is Abdul Rahim bin Sharifuddin, Ahmad Razin bin Jeffrydin, myself Ainu Sofia binti Awi, Dayano Adlina binti Awang Karno, and Muhammad Zamir bin Norman. For the introduction of this project, I would like to explain the background and purpose of the program developed. This project involved the development of a Python-based computational tool that is used to analyze statically indeterminate structure using a moment distribution method. In civil engineering, this method is widely applied, especially for continuous beam and frame. However, when solved manually, the calculations are often complex, time-consuming, and prone to error. Because of that, Python was selected as the programming language due to its simplicity, versatility, and strong capability in handling numerical and engineering-based algorithms. The program was developed by Jupyter Notebook, which allowed the code to be executed step by step. This makes the entire calculation process more visible and easier to debug. The software emphasizes structure, data input, iterative computation, and systematic output generation. Users are required to input key structural information such as geometry, material properties, apply load, and support condition. Based on this input, the program calculates fixed and moment, stiffness factor, and carryover factor for each structural member. The moments are then distributed and balanced iteratively using loop, and control structure using convergence is achieved within a specific tolerance, ensuring accurate and reliable result. In addition, input validation is included in the program to ensure the accuracy of user input and the reliability of the final analysis.
The objectives are to calculate support reactions and moments using the moment distribution method in Python, validate the results against manual calculations, and develop a flexible tool for imputing loads, boundary conditions, and beam dimensions.
Next is the problem statement. In civil and structural engineering education, students are required to analyze beam structure, including statically indeterminate beam. One common method used is the moment distribution method. However, this method involves many repetitive steps and detailed calculation, which often cause confusion and calculation error when done manually. At the same time, students are learning programming skills such as Python, but many find it difficult to apply this skill to structural analysis problem. There is a lack of learning tools that effectively combine programming with beam analysis, making it hard for students to verify results and understand structural behavior. Therefore, this project aims to address this gap by integrating Python programming with the moment distribution method, helping students reduce manual error, improve understanding, and develop computational skills that are relevant to modern engineering practice.
This flowchart shows the overall process of how the Python program analyzes a beam using the moment distribution method. The process starts by inputting the beam data, which include the span length, EI value, load magnitude, and position, and also the support condition. These inputs are very important because they define the structural behavior of the beam. Next, the program determines the degree of indeterminacy of the structure to confirm that the structure is statically indeterminate and suitable for moment distribution analysis. After that, all joints are initially assumed to be fixed. This assumption is necessary in the moment distribution method to allow the calculation of fixed and moment. The program then calculates the member stiffness using the appropriate stiffness equation such as EI over L or 2EI over L, depending on the support condition at each end. Once the stiffness value are obtained, the distribution factor at each joint are calculated by dividing the stiffness of each member by total stiffness at the joint. This distribution factor determines how the unbalanced moment are distributed among connected members. The next step is the calculation of fixed end moment due to applied loads, such as point load and uniformly distributed loads. This fixed end moment represents the moment that will exist if the beam end will be fully fixed. After obtaining the fixed end moment, the moment distribution iteration process begins. At each joint, the program checks whether the joint moment is balanced or not. If the joint moment is not balanced, the unbalanced moment are distributed according to the calculated distribution factor. Then the carryover factor, which is typically 0.5, is applied to transfer moment to the adjacent end of the members. This iteration process is repeated until the joint moment become balanced within an acceptable tolerance. Once the joint moment are balanced, the program proceeds to calculate the support reaction by satisfying the equilibrium equation, such as the sum of vertical force and the sum of moment being equal to 0. Finally, based on the calculated reaction and moments, the program constructs the shear force diagram and bending moment diagram. This allows user to clearly visualize the internal force and bending behavior of the beam. The process then ends with the final analysis result.
Next, for the manual calculation. For this project, I first carry out the manual calculation using the moment distribution method to analyze the statically indeterminate beam. The first step is to determine the distribution factor at joints A, B, and C. This is done by calculating the relative stiffness of each connected member at the joint based on their flexural rigidity and span length. The distribution factor for each member is obtained by dividing its stiffness by the total stiffness at that joint. This distribution factor controls how the unbalanced moment is distributed to each member. The second step is to calculate the fixed end moment for each beam span due to the applied load. Using standard formula, the fixed end moment obtained are negative 45 kN and negative 66.86 kN, where the negative sign indicate hogging moments at the support. Next, using the fixed end moment and distribution factor, a moment distribution table is constructed. At each joint, the unbalanced moment is distributed to the connected member according to their distribution factor, and the corresponding carryover moment are applied to the far ends of the member. This process is repeated until the moment becomes sufficiently small. Finally, the distributed moments are summed to obtain the final end moment for each member, completing the manual analysis of the beam. For the final step of the manual calculation, I determine the support reaction for span AB and span BC. Using the final end moment obtained from the moment distribution table, I apply the equilibrium equation, where the sum of vertical forces and the sum of moment for each span must be 0. By taking moment about the support and considering the applied load together with the end moment, the reaction at each support were calculated, and the final reaction values for span AB and span BC are shown on the slide.
Next is Python program results. The analysis begins with a Python-based program designed to automate beam analysis using the moment distribution method. Users are first required to input key structural parameters, including point loads, uniformly distributed loads, and span length. Using this input, the program computes the fixed end moment for each beam segment. This moment represents the initial internal force, assuming both ends of the members are fully fixed. The fixed end moment serves as the starting point for the subsequent moment redistribution process. Once the fixed end moment are established, The program applies the moment distribution method to achieve equilibrium at each joint. The stiffness of each connected member is first evaluated, allowing the distribution factors to be determined accurately. These factors control how unbalanced moments are shared between members at a joint. Balancing moments are then calculated and distributed accordingly, while carryover moments are transferred to adjacent members. This entire procedure is evaluated iteratively using a loop structure, continuing until the remaining unbalanced moments fall within a predefined tolerance. After convergence is reached, the program combines the fixed end moment, balancing moment, and carryover moment to obtain the final end moment for each beam member. With the internal moments fully determined, the program proceeds to calculate the support reaction based on static equilibrium principle. This reaction represents the force transfer from the beam to its support. All results are presented clearly in standard engineering units, allowing for straightforward interpretation and verification. This output is generated from a Python program that has been developed. User input data such as point load, uniformly distributed load, and span length are used to produce the program outputs, which is fixed end moment and distribution factor. In addition, iterative outputs are generated to illustrate the calculation process involving the fixed end moment, carryover factor, and the moment distribution process until the final results are obtained. Although this Python program functions well, there are still issues related to numerical roundings, particularly during iteration process. The iterations show roundings errors that cause variation in the output, such as differences in the fixed end moment compared to manual calculation. As a result, the support reaction output also change. However, the obtained values remain approximately similar to those calculated manually.
Assalamualaikum. So, both methods were compared using identical input and boundary conditions and showed good agreement. The manual results that we got for RB1 was 54.97 kN and RC we got 114.6 kN, while the Python analysis produced was RB1 we got 50 kN and RC we got 114.63 kN. The small differences are mainly due to rounding and numerical approximations and are acceptable for engineering analysis, confirming the reliability of the method.
Assalamualaikum, my name is Dayang Nur Adlina. My number metric is CF240146 and I will explain the user manual for the developed program. The program is designed to perform analysis based on the data entered by the user. First, users are required to input the necessary data in the input section provided. Once all inputs are completed, the program is executed by clicking the Run button. The system will automatically process the data based on the program algorithm. Finally, the results are displayed in the output section, which can be used for interpretation, analysis, and reporting purposes. That's all from me. Thank you.
In the nutshell, this project developed a Python-based tool using the moment distribution method to analyze indeterminate structures. The results closely match manual calculations, confirming the accuracy and reliability of the program. Minor differences are negligible for engineering use, validating the method for future structural analysis and also decision making. So this is our references. That is all from us. Thank you very much.